Have you ever really thought about the difference between just knowing a distance and actually knowing the way to get somewhere? Well, that simple idea is at the very heart of one of the most powerful tools in all of science, vectors. And trust me, if you've ever used a map on your phone, you're already using them without even knowing it.
Okay, let's just jump right into it with this question. If I tell you, the store is 5 kilometers away, well, that's nice, but it's not super helpful, right? You could walk 5 kilometers in a circle and never find it. But if I say, the store is 5 kilometers north, now you've got everything you need. You've got the distance, and you have the direction. You know exactly where you're going. And that one crucial little difference, that little piece of information about direction, is exactly what separates two really fundamental types of quantities in the world of physics and math, scalars and vectors. So on one side you have scalars. These are the simple ones. They're really just a number, a magnitude, a size. Think about things like temperature, or how much you weigh, or the price of a gallon of milk. But on the other side, you've got vectors. And vectors, well, they're the whole package. They have that same magnitude, that size, but they also come with a specific direction. All right, let's put this to the test to really get a handle on it. How about a quick little game? I'm going to throw out a few examples, and you just think to yourself, is it a scalar or is it a vector? Ready?
Okay, first up, a boat moving at 35 kilometers per hour east. That's for sure a vector. We've got the speed and the all-important direction. Next, a baby's mass of 2.9 kilograms. That's a scalar. It's just a number. There's no direction to it. Now here's a fun one. A race car doing 220 kilometers per hour on an oval track. It's a vector. Even though the speed is constant, its direction is changing every single second. A hot cup of coffee? Definitely a scalar. And finally, a force needed to lift a container? That's a vector, because that force has to be applied in a very specific direction, up.
Awesome. So now that we can kind of spot vectors out in the wild, let's actually break one down. Let's look at its anatomy and see what it's made of.
So the official textbook definition is nice and clean. It's just a quantity that has both a size and a direction. And the key part, the part that makes it so useful, is how we draw it, as a directed line segment, or, an arrow.
And this picture just says it all, doesn't it? An arrow is the perfect way to visualize this. A vector has a starting point, which we call the tail, and an end point, the tip or the head. How long the arrow is, that's its magnitude. A longer arrow means a bigger number. And of course, whichever way the arrow is pointing, well, that's its direction. Simple, but so powerful. So we have this arrow. But in math and physics, we need to be a little more precise than just long or pointing that way. So how do we formally define those two key parts, the size and the direction? Well, when we want to talk only about the size of the vector, just its length, we use a special notation. We put these bars around it that look just like absolute value signs. This is our signal to everyone that for a moment, we're totally ignoring the direction and just focusing on the how much. And for direction, we need to be super precise. You can't just say up and to the right. We use systems that work like a compass. You've got true bearings, which measure the angle clockwise from north, and quadrant bearings, which use angles from the north-south line. This gives every single vector a unique address, a direction that anyone, anywhere can understand.
Now this is where it starts to get really interesting. Once you have a bunch of these vectors floating around, you can start to see how they relate to one another. They kind of have their own little family relationships, all based on their size and direction.
First up, you've got equivalent vectors. Think of these as identical twins. They have the exact same length and point in the exact same direction. Now, the really important thing here is that it doesn't matter where they are. One could be here, one could be way over there. If their length and direction match up, we consider them equal.
And then you have the opposite vectors. They share that same magnitude, their arrows are the same length, but they're heading in perfectly opposite directions. One is doing a complete 180 of the other. It's the exact reverse.
And finally, there are parallel vectors. This is the broadest category in the family. To be parallel, vectors just have to be on the same line of travel. They can point in the same direction or the opposite direction. And here's the kicker. Their magnitudes, their lengths, don't have to be the same at all.
So we've got all these definitions, all these rules, which leads us to the big question. So what? Why does any of this matter? Where do we actually see vectors in action? The short answer? Literally everywhere. The entire world of physics is built on vectors. The force of gravity pulling you down into your chair right now is a vector. The friction from the floor that keeps you from slipping is a vector. Every single push, every pull, every force you can possibly think of has both a strength and a direction.
And that is why this is so absolutely crucial. Look, if you want to be an engineer designing a bridge, or a pilot navigating an airplane through the wind, or even a programmer building the 3D world of a video game, you have to understand vectors. They are the fundamental language we use to describe how everything moves and interacts.
So I'll leave you with a little puzzle to chew on. Take a look at this shape. Now that you know the rules, ask yourself, is the vector going from point A to point G the same as the vector from point C to point E? Are they equivalent? Remember the definition. It's not about where they start or end. It's about having the exact same magnitude and the exact same direction. Have a good think on that one.